Hello, my name is Elvis Palma, and it is my pleasure to present our capstone project, Rust versus C++ Embedded Systems by General Dynamics. The group is composed by Hunter Belden, Pranav Nadingpali, Elvis Palma, myself, and Ross Potter. Hunter is going to present how C++ compares to Rust while taking real-time audio. Ross is going to present a comparison using a heartbeat sensor, and Pranav is going to present a comparison with network communication. However, to start, this is an overpressure simulation. What we're trying to do here is to simulate an overpressure environment and see how C++ will compare to Rust. And the point is to see how safe the two systems will be in comparison to one another. Right now, what we can see is the pressure building up at the pump, and the relay would activate the solenoid to release the pressure, and our system would calculate how long would it take to release the overpressure situation. So what we can see on the screen right now is the pressure building up, and it's cycling right now between high pressure and low pressure. So what we are calculating, and Pranav is gonna display soon, is how the two embedded systems will react, C++ versus Rust. Without further ado, Pranav is gonna show the actual data between the two comparisons.
Hey, I'm Pranav, and I'm going to go over the pressure sensor results and then go into networking experience. So for the pressure sensor, we wanted to measure latency and sample rate, and in order to measure the latency, we essentially have to turn the pump on and see how long it will take to get a reading over I squared C. To measure the sample rate, we essentially measure how many readings we got across I squared C when we measured across an interval of turning the pump on. So here are the sampling rate results, and we can see that Rust and C++ performed essentially the same, except in the very top percentile, where other factors came into play, such as the operating system and the hardware variance. Here we can see in the pressure latency rate, we can see that the latency is also about the same between Rust and C++. And so basically, we're able to conclude that Rust and C++ are able to perform essentially the same when doing IO-bound tasks, such as interacting over I squared C. So the next experiment we worked on, that I specifically worked on, was networking, and our goal was to compare the performance of Rust and C++ in their terms of their networking capabilities. In order to do this, we created our own network interface using Linux that exposes raw Ethernet packets. We then wrote our own custom IP and TCP implementation in both Rust and C++ to parse those packets, and we then measured across millions of requests the latency, throughput, and number of concurrent connections we're able to handle. So here we're looking at the latencies, and we can see that Rust and C++ perform similar, but C++ is able to perform slightly better on both the average P95 and P99. Here's the throughput, and we can see that C++ has slightly higher throughput than Rust too. And here are the amount of concurrent connections we're able to handle. Here we can see that C++ performs slightly better than Rust on concurrent connections. And I'll go over why we can see a C++ is winning in pretty much all of these cases. So here I'm showing some specific examples. So whenever we're accessing a buffer in C++, we're able to pretty much just do it raw, while in Rust, in order to do it safely, we have to use this RC_ref_cell, which simply does reference counting at runtime, which adds runtime overhead. And in Rust, whenever we index into a buffer, it does a balance check to make sure that index is within the buffer's range. And this also adds a runtime overhead, while in Rust, we don't have, while in C++, we don't have to do that. So essentially, we can see here that C++ slightly outperforms Rust due to some overhead that Rust has at runtime to ensure memory safety. However, the user could easily use non-idiomatic unsafe Rust code to just perform just as good as C++.
Hello, my name is Hunter Belton. I am with Team 30, General Dynamics. Our project focuses on Rust versus C++ in real-time systems. My demo setup is a Raspberry Pi 4 Model B, 2 GB of RAM, running Debian GNU Linux as the OS, as well as two 7-inch monitors, 800 by 400, USB microphone, cabling for HDMI and power. Here we have a video of the two programs running simultaneously, C++ on the left, Rust on the right. You'll see a waterfall diagram as well as a spectrogram, as well as two plots at the bottom, one for fast Fourier transform in time, as well as peak frequency in hertz. You are going to see the differences between the two, as well as the graphs. The waterfall graphs do specifically look a little bit alike, but the insufficiencies of C++ will show on the left. What the demo showcases overall. Real-time audio capture. Both Rust and C++ read live PCM audio from the microphone and demonstrate real-time data handling. Real-time FFT, fast Fourier transform. 2048 point FFT computed continuously. Rust using Rust FFT, and C++ uses FFTW3, showcasing high-performance digital signal processing. You will see a waterfall spectrogram, rolling time frequency display, color-coded for intensity mapping purposes, demonstrating real-time rendering, efficient memory reuse, and stable drawing pipelines. What's showcased for the C++? Unsynchronized shared buffer, G input buffer, legal to compile, undefined at runtime, audio callback, writing while main thread reads causing corrupted FFT frames, occasional wrong FFT data, if buffer reads during writes, simulating silent data corruption, race conditions, concurrency bugs, manual memory errors, leaving leaks, crashes, and undefined behavior. Total freedom equals total responsibility, and this showcases that with C++. 4. Rust prevents all from the last slide due to argmutex, borrow checker rules, thread safe architecture, resource acquisition is initialization mandatory, ownership model, automatic cleanup, zero leaks guaranteed, overall showcasing Rust's superior benefits, thread safety, memory safety, no undefined behavior, safe concurrency, clean API, and predictable behavior from Rust.
Hi, everyone. My name is Ross Potter, and I am responsible for part of the data analytics, open source GitHub architecture, and memory management analysis for Team 30's Rust vs. C++ capstone project. My responsibilities were building the GitHub and GistHub structures for our experimental code, managing the AWS test results for edge case scenarios, and analyzing how Rust memory model impacts real-time electronics compared to C++. In real-time systems, memory errors aren't just software bugs. They can cause real-world failures. Google's OSS fuzz has found over tens of thousands of real memory corruption bugs in C and C++ software. The famous Heartbleed incident was caused by a simple C buffer overread, which is exactly the kind of bug Rust bounds checking would have prevented. C++ allows leaks, dangling pointers, and race conditions, which can freeze or crash a device. Our buffer fuzz in Linux AWS showed C++ failing around 47,000 iterations due to unsafe memory access, whereas Rust completed similar workloads without corrupting that memory. I processed thousands of timing, memory, and crash data points from my Raspberry Pi fuzzing environment. C++ had multiple crashes, unpredictable timing spikes, and memory drift as shown in the graph, while Rust showed nearly perfect stability throughout. I built the CSV pipeline, generated the graphs, and created the analytical charts that our team used to help draw these conclusions. I also documented a Raspberry Pi hardware setup, including the Pi board display and the server support. And this was essential for verifying our AWS data and our real-time data, matching it to real-world system behavior while providing an easier visual for information to be displayed. To validate the results, I deployed both C++ and Rust services onto a Raspberry Pi, where I recorded heartbeat signals, uptimes, and flatline counts in live display that also records to a CSV file. You can see the difference clearly as C++ drops out and produces flatlines while Rust maintains a stable heartbeat throughout. My analysis showed that Rust memory safety rules directly translate into stability for real-time systems. C++ can be extremely fast, but even tiny memory bugs cause these resets or freezes. Rust avoids those failures by design. C++ can be programmed to manage that memory on its own, but Rust avoids all of that without having to worry about that management.
And that concludes our presentation. In summary, Rust is more reliable than C++ in many instances, and the compromises in speed can be negligible in most cases, and in other cases, Rust could actually even outperform C++ by being more reliable and faster. We hope that this research can help the industry decide whether making a switch to Rust is well worth it, and it has been our pleasure to work on this project. and present it to you. Thank you very much. Bye.